In this video, we're going to describe potency in terms of binding equilibria. We will also calculate a binding energy. Potency refers to the concentration of a molecule that is required to exert its effect. EC50 and IC50 are both measures of potency. EC50 is a concentration, the concentration at which an agonist or partial agonist generates half its response. IC50 is a concentration, the concentration at which an enzyme inhibitor or an antagonist blocks the action of an enzyme or receptor respectively. Let's add another curve with AB labels to our graph on the left. Both these curves have EC50 values. We would say that molecule A is more potent because it exerts its effect at a lower concentration. Molecule A has a lower EC50 than molecule B. Molecule A is more potent. Drug-target binding is a reversible process typically. The more the equilibrium from this reversible binding favors the drug-target complex, the more potent a drug will be. To the right is the equation for this equilibrium. K is the equilibrium constant. For agonists, this K, the equilibrium constant, is often called Kd, the dissociation equilibrium constant. For enzyme inhibitors and antagonists, it is Ki, the inhibitory equilibrium constant. Ki and Kd can be measured through calorimetry experiments. Both Ki and Kd are measures of potency. Smaller K values indicate higher potency. For bioactive molecules, Kd and Ki are very low. For example, a typical hit from a screening program might have a Ki or Kd of 10 to the minus 6 molar. That's 1 micromolar. A representative drug might have a Ki or Kd of 10 to the minus 8th molar, or about 10 nanomolar. On the screen is an equation that relates equilibrium constants to the binding energy between a molecule and its target protein. DeltaG bind is our binding energy. K is our Kd or Ki. Note that we use 1 over K in this equation because binding is the reverse of dissociation. Diphenhydramine is a histamine H1 receptor antagonist with a Ki of 13 nanomolar, or 1.3 times 10 to the minus 8th molar. Our units must be molarity for this equation to work. If we go through the calculation of DeltaG with appropriate values for R and T with appropriate units, we get a binding energy of diphenhydramine for the H1 receptor of minus 10.8 kcal per mole based on its experimental Ki value. Binding energies for drugs are always negative, although the negative sign is sometimes omitted. In this video, we learned how to think about potency in terms of binding energy and binding equilibrium, and we also saw how to do a calculation of a molecule's binding energy based on its potency, its K value.